Right, how are you? Again, let us look at theorem 3, the division by t. Now, what does the division by t state? It states that if the limit as t approaches 0 on f of t over t exists. Now we know that the limit will only exist for the L'Hopital's rule. For these problems, the limit will only exist for the L'Hopital's rule. So what we are going to say, we say that the Laplace transform of f of t divided by t is equals to an integral from s to infinity of f of sigma d sigma. What you need to know about this sigma here, this sigma, it is called the dummy variable. In other example, I'll replace sigma. I'll try to use some tau. I'll try to use k as different variables. Some gamma if I want to. So all of these will be used as dummy variables. Now, what is the proof on this theorem? So, because every theorem must be given a proof. So the proof will be the integral from s to infinity of f of sigma d sigma is equals to an integral from s to infinity. Now we only know that to get the f of sigma, let us say that the Laplace transform of f of t, it is going to be f of sigma. It's an example. Let us say that. So if we say that, we are going to have in bracket an integral from 0 to infinity of f of t e to the power negative sigma t dt d sigma. Now in this case, we're introduced to something called the double integral. Now a double integral, it's an integral of this format. So if you are writing it in a proper format, I'm going to have an integral from s to infinity, integral from 0 to infinity of f of t e to the power negative sigma t dt d sigma. But if you can clearly see, this does not get us anywhere. Now, what can happen is that we can interchange the integral. How can we interchange the integral? What do I mean by that? I mean that we are going to have an integral f of t e to the power negative sigma t d sigma dt. Now you can notice that I have left the bounds of integration. Since I have left the bounds of integration, what do I mean? I need to draw the diagram that represents the bounds in the original diagram here. So if I draw the region using that, the first one, you can clearly see that your t, let's say t is here. When t is 0 and t is infinite, right? Let's go to sigma. Let's say sigma, it is the y-axis. Now the sigma is equals to s. It's a straight line like that. And then sigma is equals to infinite. It's somewhere here, right? You can see that you have bounded this thing in this format, in a triangular thing. I know that you cannot explain or you cannot hear what I'm doing. It's called the change of order. So let's say this one, it's represented by s is equals to sigma. This one here, it is 0 is to 0. That one there, it is infinite to 0. That one there is infinite is to infinite. So a diagram given in this manner can explain how to interchange. I know that we are not introduced to double integrals as yet, but the idea comes here. Now, what is going to happen then? Now, since you have changed the order of integration, also the bounds must change. Now, from this thing, now it's starting, because I said this one is sigma, this one is t. Now, sigma arco will start where? Your sigma will start where? Sigma will move in this order. So I'm going to have what? I am going to have from S to infinite. And then your t will start where? From 0 to infinite. So it does not change anything because there's infinite there. But the explanation of this change of order, you need to draw the triangle. But you can just take this integral, place it here, take this integral, place it there. Done. So the next thing that you need to do, since we are integrating in terms of sigma, this f of t is just a constant. So I'm going to have an integral from 0 to infinite of f of t, integral of s to infinite of e to the power negative sigma t d sigma dt. Right? Now let us use other properties of improper integrals. So I'm going to have integral from 0 to infinite. This is just a proof, guys. This is just a proof. So it's an integral from 0 to infinite of f of t, and then we are going to have the limit as k approaches infinite on an integral from s to k e to the power negative sigma t d sigma dt. So when we try to integrate that, we have an integral from 0 to infinite of f of t. So now I'm going to have the limit as k approaches infinite of, what is an integral of e to the power negative sigma t? That is just going to be negative 1 over t e to the power negative sigma t between s and k dt, and then substitute the bounds. It's not infinite, it's just k. Integral from 0 to infinite of f of t, the limit of k approaches infinite on negative 1 over t e to the power negative k t plus 1 over t e to the power negative st dt. Now, you know that whenever you approach infinite here, this entire thing will just become 0. So in that case, I'm going to have an integral from 0 to infinite of f of t 1 times 1 over t e to the power negative st dt, right? 1 over st dt. So what you can clearly see is that because we're integrating in terms of t here, it's an integral from 0 to infinite of 1 over t f of t e to the power negative st dt. This thing here is the same thing as the Laplace transform of f of t all divided by t. So this is just a proof regarding the first theorem. Now, do not worry about the theorem. It's just an explanation on YouTube. Now, your work will start here. The first thing that you are going to do, it is to find the Laplace transform of 3 minus e to the power 2t divided by t. Now, I'm just going to provide here a lot of explanation. A lot of explanation. Please, 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 please make sure that you listen carefully, because there is a lot that you need to understand here. There is an integration that is going to be involved here, right? So please make sure that you listen carefully, right? What is the first step when you are looking at on your third theorem? The first thing first that you need to do, you need to take the limit as t approaches 0 on 3 minus e to the power 2t divided by t. When you substitute this 3, when you substitute this 0 inside here, you can clearly see this. I'm going to have 3 minus 1 divided by 0, which is 2 over 0. Because you have this form, which is called the indeterminate form, you cannot say the limit is going to be undefined. But what you can actually do, we need to first find, the first thing that you need to do, we need to first find the L'Hopital's rule. We need to use the L'Hopital's rule. So what we are going to do now, we are going to say the limit as t approaches 0 on. Derive the numerator, it's going to be negative 2e to the power 2t. Derive the denominator, it's 0. And now, it's 1, sorry. And now you need to substitute your 0. When you substitute your 0, I'm going to get negative 2. What does it mean? It means that the limit exists. Because now the limit exists, because the theorem says that, because now the limit exists, we need to proceed. How will we proceed? The second step that we need to do, we need to find the Laplace transform of the original problem numerator. We need to find the Laplace transform of this thing here. We need to go to the original problem and find the Laplace transform of the numerator. So we need to find the Laplace transform of what? Of 3 minus e to the power 2t. What is the Laplace transform of 3 minus e to the power 2t? We know that the Laplace transform is linear, so we can find the Laplace transform of 3. What is the Laplace transform of 3? That is going to be 3 over s minus. What is the Laplace transform of e to the power 2t? That is just 1 over s minus 2. You think that you are done. No, you are not done. Because what we have done, we are only here in the problem. We need to now go to the third theorem. Now, the third theorem states that after you have found the Laplace transform of the numerator, you need to replace s with the dummy variable and integrate what you have. Do you understand that? After you have find the Laplace transform of the numerator, you need to replace that s that you have and integrate this thing in terms of the dummy variable. So now I'm going to have an integral from s to infinity. You are going to choose your dummy variable. Let us first say it's going to be 3 over sigma minus 1 over sigma minus 2 d sigma. So after I find the Laplace transform of the numerator, replace s with a dummy variable and then integrate it from the bounds from s to infinity. So what is an integral? What is an integral of 3 over sigma d sigma? It's going to be 3 ln sigma minus, what is an integral of 1 over sigma minus 2? It's going to be ln sigma minus 2. Please keep these integration things in mind. Integration of 1 over x dx was ln of x plus c. The integration of a over x plus b plus or minus b dx was a ln x plus or minus b plus c. Like that. So the next thing that we need to do, we need to write this as a single between the bounds of s and infinity, because we need to substitute the bounds. So what we're going to have here now, I'm going to have let us say it is ln sigma cubed minus ln sigma minus 2 between s and infinite. And then I'm just going to use my laws. Remember the laws of logarithms. ln a plus ln b. ln a plus ln b is what? It is ln a times b. And then ln of a minus the ln of b is just going to be ln of a over b. So that are the rules that you need to keep in mind. So we need to perform them here. Why do we perform here? Because of this infinite. Because of that infinite. So I am going to have what? I'm going to have ln sigma cubed divided by sigma minus 2 between s and infinite. By the way, when you substitute this infinite in here, this entire thing will become 0. That entire thing will become what? Will become 0. That entire thing that you see there is going to become what? It is going to become 0. So I'm going to have here 0 minus. When you substitute this s here, I'm going to have 0 minus the ln of s cubed divided by s minus 2. So your final answer in this problem is going to be ln s minus 2 divided by s cubed. The reason you have swapped it is because of this negative outside. Right, let us do another example. I would love us to do a lot of examples in this theorem. I don't care that you are going to have a lot. I don't care that it's going to be more minutes, but let's just do the Laplace transform. So the Laplace transform. The Laplace transform of e to the power 7 minus e to the power negative 4t all divided by t. What is the first thing that you need to do there? We need to take the limit, but the L'Hopital's limit. The limit as t approaches 0. We need to derive the numerator. The derivative of the numerator is what? It is 7 e to the power 7t minus the derivative of the other term. It's plus 4 e to the power negative 4t divided by 1. And then when you substitute 0 on t, I'm going to have 13. I'm going to have 11, by the way. So the limit exists. The limit exists. I'm not explaining this part a lot is because it's not part of the work, really. We know that the limit exists. Actually, the markers know that the limit exists. So the main thing that is happening here, you need to know how to find the Laplace transform. After I find the limit, what is the next thing that you need to do? You need to find the Laplace transform of the numerator of the original problem. So I'm going to find the Laplace transform of e to the power 7t minus e to the power negative 4t. What is the Laplace transform of e to the power 7t minus e to the power 4t? It is going to be 1 over s minus 7 minus 1 over s plus 4. This is the Laplace transform of the numerator. What is the next thing after you find the Laplace transform of the numerator? Where there is an s, replace s with a dummy variable. So what I'm going to do, I'm going to have an integral from s to infinite of 1 over k minus 7 minus 1 over k plus 4 dk, like that. We do not care what type of variable are you using, but do not use t and s. We do not care what type of variables are you using, but do not use t and s. So what I'm going to do now, I need to integrate that. We need to remember these rules of integration here. So what is an integral of 1 over k minus 7? That is just ln k minus 7 minus, what is the integral of 1 over k plus 4? It is ln k plus 4 between s and infinite. And then the limit, it's going to be k minus 7 divided by k plus 4. And then between s and infinite. But by law, you know that when you substitute infinite to ln, this entire thing is going to be 0. This thing is going to be 0. This thing is going to be 0. So I'm going to have here 0 minus minus what? Minus the ln of s minus 7 divided by s plus 4. Which is, because there is a negative outside, I need to have an ln, take the numerator, put it outside, put it on the numerator, take the numerator, put it on the denominator. So I'm going to have s plus 4 over s minus 7. So this is your answer. Now you may ask why I am saying that the limit will become 0 if you substitute infinite. Let's just look at this. Let us find the limit as k approaches infinite on ln k minus 7 over k plus 4. I want to give you an example of why I'm saying it's always 0. The reason it's always 0 because we need to remember that whenever we take the limit as something goes to infinite, we go to the denominator and look for the highest exponent. What is the highest exponent that you're going to have there? It's going to be what? It's going to be k. I'm going to take this k in this denominator. I'm going to divide everything that I see there with k. So what do I mean by that? I'm going to have the ln, I'm going to have the limit as k approaches infinite on ln 1 minus 7 over k over 1 plus 4 over k. Now you understand again that when you substitute infinite to the denominator, the entire thing goes to 0, right? When you substitute infinite to this denominator, the entire thing goes to 0. So you are going to be left with ln 1 over 1, which is the same thing as ln 1. What is ln 1? 0. So whenever you're going to have this ln, then there's an infinite substitution in it. Just know that the answer is always going to be what? It's always going to be 0. Right? I think that I've made myself clear on that. Now let us look at another example. Another example is going to be quite tricky, but please make sure that you listen. Listen very carefully. So the second one, or the third one, it's the Laplace transform of cos 4t minus sine 7t all divided by t. You know by now that to find the Laplace transform of this, we need to find the limit. So the limit as t approaches 0, but we need to do the L'Hopital's rule. Derive the numerator. The derivative of the numerator is going to be 4 sine 4t minus 7 cos 7t divided by 1. The answer that you're going to get here is just 7, negative 7. So the limit exists. So what is the next thing that you need to do? We need to find the Laplace transform of the numerator. What is the Laplace transform of that numerator that you're going to have there? So the Laplace transform of cos 4t minus the Laplace transform of sine 7t. What is the Laplace transform of cos 4t? It's going to be s over s squared minus 16 minus, what is the Laplace transform of sine 7t? That is going to be 7 over s squared minus 49. After we have found the Laplace transform of this, what you need to do, we need to integrate this part. Where there is x, I need to replace it with the dummy variable. I'm just going to choose another dummy variable. So I'm going to integrate this from s to infinite. But now I'm going to have v over v squared minus 16 minus 7 over v squared minus 49 dv. It's just going to change. There is no need. You can write any letter you want, but run away from s and t. Now, how do we integrate such a thing? We use integration by parts. How do we integrate such a thing? We use partial fractions. Now, I'm going to give you a trick. When you integrate f prime of x divided by f of x dx here, Your answer to this, let's say to a power of an exponent a. Your answer to this, it is 1 over a ln f of x plus c. What does it mean? It means that when you integrate a derivative over the original function, we have a derivative over the original function, because what is the derivative of v squared minus 16? It's just 2v, right? So what we are expecting you to do, we need you to expect that the integral of this part is just going to be 1 over 2 ln v squared minus 16. That is the Laplace transform of that. And there is no need of doing partial fractions here, because you understand that the denominator of this is the numerator's derivative. And then minus. How do we get to find the derivative of that? So there we are now going to do some partial fractions. So it's going to be 7 over v minus 7, v plus 7. So this is going to be a over v minus 7 plus b over v plus 7. Now, what makes the denominator of a 0? We are going to do something called the cover-up rule. What makes that denominator 0? What makes the denominator of a 0, guys? This denominator here. What makes the denominator of a 0? It's going to be 7, right? So we are going to cover this denominator here. So we need to cover it here. By covering it, we are left with 7 over v plus 7. Substitute the number that makes the denominator 0. So I'm going to have 7 over 7 plus 7, which is 1 over 2. To b, what makes the denominator b equal 0? It is minus 7. Cover this, and you are going to be left with what? With 7 over v minus 7. Where there is a v, substitute negative 7, I'm going to get negative 1 over 2. So it is going to be 1 over 2 ln v minus 7. Let me just rewrite this, because you are not going to understand what happened. So now I'm going to have an integral from s to infinity of v over v squared minus 16 minus in bracket 1 over 2 1 over v minus 7 minus 1 over 2 1 over v plus 7 dv. So an integral of s to infinity v over v squared minus 16 minus 1 over 2 in bracket 1 over v minus 7 minus 1 over v plus 7 dv. Now, what is an integral of v over v squared minus 16? The integral of that is just going to be 1 over 2 ln v squared minus 16 minus 1 over 2 in bracket the ln of v minus 7 minus the ln of v plus 7 between s and infinity. So it's 1 over 2. We can simplify this, so I'm going to have ln the square root of v squared minus 16 minus the ln square root of v minus 7 over v plus 7 between s and infinity. And what you can clearly see here is that you can rewrite these limits as a single sum. So now I can have the limit. I can have ln over what is going to happen? I'm just going to use my algebraic knowledge. So it's going to be v squared minus 16 times the square root of v plus 7 divided by the square root of v minus 7 between s and infinity. Now you know this thing is going to be, and it's going to be 0 for some point, right? And then the final answer here, I'm going to take this s and substitute it in, because if you substitute this infinite, this thing is going to be 0 and there'll be a minus outside. What you need to know or you need to understand is that your final answer should be a big square root of s minus 7 divided by s squared minus 16 s plus 7. That should be your final answer. But in a major test, guys, just make sure that you're only going to be given cosh or shine or sign. So just keep this in mind, that this is the full process. I'm only going to do the hard problems here, not the easy ones. I'm just going to do the hard problems. So again, the Laplace transform of what? Of sine 3t minus cos 3t divided by t. In a major test, you can only be given the Laplace transform of sine 3t over t. Here, I'm doing everything. The reason I'm doing everything is because I want you to understand what is going on here. So the first thing that you need to do, you need to find the limit as t approaches 0, but using the L'Hopitals. So I'm going to have 3 cos 3t minus 3 sine 3t positive divided by 1. Your final answer here is just going to be 3. So it exists. What is the next thing that you need to do? We need to find the Laplace transform of what? Of sine 3t minus cos 3t. What is the Laplace transform of sine 3t? That is just going to be 3 over s squared plus 9 minus, what is the Laplace transform of sine of cos 3t? It's going to be s over s squared plus 9. Like that. So after I find the Laplace transform, what is the next thing that you need to do? We need to change that s and put it into an integral sign. So I'm going to integrate from s to infinite 3 over tau squared plus 9 minus tau over tau squared plus 9 d tau. Now, what is an integral of 3 over tau squared plus 9? Keep this in mind here. The integral of 1 over of a over x squared plus b squared dx was what? Remember, it was a over 1 over b arctangent x over b plus c. It was something like that. So here it's going to be 3 over 1 over 3, because you need to take the square root of 9. The arctangent of tau over 3, like that, minus, what is the Laplace transform of tau over tau squared plus 9? It's going to be minus 1 over 2 ln tau squared plus 9 between s and infinite. So the 3 will cancel. So I'm going to have the arctangent of tau over 3 minus ln square root tau squared plus 9 between s and infinite. Now, when you substitute infinite to the arctangent, what do you think is going to happen? What will be your answer? What is the answer of infinite? The answer is pi over 2. Why? Because infinite is undefined, right? So where is tan undefined? At pi over 2. So you need to keep that in mind. So So I'm going to have pi over 2. When you substitute infinity to ln, the answer is 0, you know that. The answer is just 0. So now it's going to be minus the arctangent of s over 3 plus the ln of the square root of s squared plus 9. So this is your final answer. Do not ask me how to find the inverse of this. I'm just going to show you on the later videos on how to find the inverse of this entire thing here. But in a nutshell, guys, this is how you find the Laplace transform of division by t. You need to just keep these rules in mind that I've written. Remember, also, I'm just going to repeat this in class to make a strong foundation, especially on partial fractions, because you are going to solve some differential equations. And on our next video, we are going to look at a periodic Laplace transform, or we are going to look at the unit step heaviside. Thank you so much.